Hey everyone, it's Aaryan from Code Labs. Before getting started, I want to thank everyone on my team and my mentor for supporting me throughout these 4 weeks. The experience has been really interesting, and I've come out of the program knowing a whole lot more about the field of artificial intelligence and the programming landscape in general compared to when I first started. For my project, I focused on a specific field of natural language processing in AI called sentiment analysis. To be exact, the project involved creating a sentiment analysis model using a specific type of AI called a long short-term memory network, or LSTM for short, which has the ability to detect sarcasm in text. But let's start by clarifying what sentiment analysis is. Looking at the big picture, sentiment analysis focuses on using AI models that have the ability to predict the underlying emotions behind text. You can find these models everywhere, from the Siri that lives in your iPhone to programs that scrape the web trying to find people's thoughts on the latest book or movie. When it comes to this specific subtype of natural language processing, most developers tend to stick to two major techniques. The first being recurrent neural networks, or RNNs, as well as the newer long short-term memory networks, or LSTMs. Both these models have the ability to remember sequences of text, as well as the context of words, but LSTMs tend to do a better job at that. So for this project, I opted to use LSTMs. So now that the model has been decided, making it actually isn't too hard. To develop this sarcasm checker, I used Python in Colab, an open source editor developed by Google. The model was trained to roughly 80% accuracy, and then it was implemented into a basic user interface with a language called Flask. Finally, the finished model was uploaded to the Amazon Web Service EC2 platform, one of the most popular services to release AI tools online. And once everything was done, here's a demo of what the application looked like. As you can see, I've developed a very basic form of a user interface for this sarcasm checker, and it actually does a surprisingly good job at creating inferences. And as you can see, it creates inferences almost instantly. So as you can see, it already checked whether my first sentence was sarcastic or not, which it wasn't. And this next sentence, it's going to create a prediction almost immediately for as well. And that's basically it. I appreciate you for watching my presentation on building a sarcasm detection system using long short-term memory networks. It's been such an amazing journey working with everyone from my team and the Code Labs community. Thanks.
Hi, my name is Eshani Chauk. I'm an incoming freshman at Georgia Tech, where I'll be studying computer science with a focus in artificial intelligence. Through the Code Labs internship, I've had the amazing opportunity to learn from my mentor, Niharika Sharma, and work with my teammates, Shreya and Aaryan. We learned about natural language processing over the last 4 weeks, and today I will talk about text generation, one of the NLP techniques we worked with. Before I get into the details of text generation, I'd like to discuss the technologies that we utilized throughout the internship. Our team coded in Google Colab, a cloud-based Jupyter Notebook environment that gives developers a place to build machine learning and deep learning models in Python. Google Colab has a shared feature much like Google Docs, so collaboration between our team was seamless. In Google Colab, we utilized TensorFlow, a deep learning library that lets developers build and train models. Along with TensorFlow, we used Keras, which is an API that runs on top of TensorFlow. It's very user-friendly, which makes working with deep neural networks easier. Text generation means training a model to generate text that emulates the writing or speaking style of the input data that the model is trained with. The text generation model constantly tries to predict the next word or character of a sequence. Some applications of text generation include composing emails, word suggestions, writing in a certain author's style, and simulating DNA sequences. In the short clip on the slide, you can see a person getting suggestions for what to write in an email based on other words in the message. So, how exactly does text generation work? We've summarized this process into 6 general steps. Step 1. Import the required libraries. We use TensorFlow, Keras, and NumPy. Step 2. Create the text corpus from a large data set. Our corpus was made up of Shakespeare's sonnets, and we used this corpus as training data for the model. Then we pre-processed the data, which is crucial for building a machine learning model because it ensures that the data is clean and easy to use. Step 3. Tokenize each line of the text so that each word is mapped to a number that the computer can understand. Step 4. Create n-grams and input sequences. We iterated through each line in the corpus to create n-gram sequences, which are sequences of n items from a line of text. For example, this sentence has been tokenized, and now a new n-gram sequence is created with the first 2 words, then another with the first 3, then another sequence with the first 4 words, and so on until the end of the line. We did this for all lines in the corpus and added them into one array. Then the sequences are pre-padded so they are the same length and have zeros in front of them. Step 5. Extract the x's, which are the seen words, and y's, which is the new word, from each sequence. Since we pre-padded each sequence, the y's will always be the last number and the x's are everything before that. We then used one-hot encoding on the y's so that the model has more expressive power to learn a probability-like number for each possible next word. It is essentially a vector that represents just the target word for each y. Step 6. Now we can finally build and train a text generation model. We used a sequential Keras model since we're stacking layers. We added an embedding layer, 2 bidirectional LSTM layers, a dropout layer, and 2 dense layers to our model. LSTMs are preferred over RNNs for this process because they can keep track of large amounts of previous data, which is extremely important in text generation. The model is compiled and fit so that it can train on the x's and y's previously determined. Once the model is done training, it can be used to predict an n number of words based on a given sample of seed text. As Aaryan mentioned, we deployed all of our models by using Flask and AWS. First, we saved and downloaded the tokenizer and text generation model from Google Colab so that it could be used locally. Then we created a Flask app with an HTML site that allows the model to run locally on a website. The website asks for seed text and the number of words to generate, and once you press submit, it will display that number of words predicted by the model. Here's a demo of this site. After the Flask app was complete, we could deploy the model to the cloud using Docker and AWS EC2 or AWS Fargate. Thank you for listening to my presentation on my team's text generation model. I am so fortunate to have learned from and worked with such an incredible team over the past 4 weeks, and I'm excited to make our models better and more advanced in the future. We've all learned so much from the internship, especially skills such as effectively collaborating and communicating in a virtual environment, actively seeking feedback to improve our work, and adaptability. Thank you again.
Hi, I'm Shreya, and I'm going to be talking about the topic modeling portion of our internship. The final portion of our internship focused on topic modeling, an unsupervised learning technique that applies heavily to natural language processing. In unsupervised learning, the input data is not marked with a certain output, unlike the previous 2 models we had been working with. Rather, the algorithm is asked to group similar examples together, a process known as clustering. This is what topic modeling does to a group of input documents. It clusters similar documents together and can identify the keywords that are commonly found in each topic. There are 2 common methods of doing this: LDA, or Latent Dirichlet Allocation, and NMF, or Non-Negative Matrix Factorization. LDA is a statistical method for performing this task and views each document as a bag of words. LDA consequently uses the keywords in each document to assign it a topic. Of course, before performing this algorithm, we had to pre-process our data by tokenizing it. We used lemmatization, a process of reducing words to their roots in order to have a much more uniform dataset. To determine the hyperparameters, or more specific elements of the model, such as the learning rate and the number of topics, we used grid search. This is a method that automatically outputs the parameters of the model with the best validation accuracy, given lists of numbers to try for each of the hyperparameters. NMF also produces a similar output but uses linear algebra techniques to create two matrices, W and H, whose product is estimated. NMF performs feature extraction and is able to output a similar topic keyword distribution. Deciding whether to use one or the other really depends on the use case, and we ended up using LDA in our final model. We also used scikit-learn to create both our tokenizer and the model itself. As we mentioned earlier, one common application of topic modeling is to cluster different documents together, which in and of itself has many real-world applications. Topic modeling can also be used to aid queries. In this process, the topic of the query is determined using our previous model, and then the Jensen-Shannon divergence, a statistical measure of similarity between two distributions, was used to determine the top 3 articles relevant to the query. In order to deploy this model, we use containerization in Amazon Web Services. We use Docker to containerize each web page so that our application's requirements and the application's image would be separated from the rest of our local environment. In addition, we can use Amazon's Fargate to deploy our web page to a public IP address and eventually a public site. If we wanted more control in terms of cloud settings, we could use Amazon's EC2 as an alternative to Amazon's Fargate. Thank you so much for listening, and our contact information is listed on this slide in case you would like to get in touch with any of us.